What if a single flick of the wrist could save the planet 14 liters of water a day? That's the promise of laminar flow, but there's a razor-thin mathematical boundary between conservation and chaos. After performing a ritual washing, you face a minor yet universal engineering dilemma: shaking excess water from your hands. The goal is to transfer the water film from the dermis to the ceramic basin without transforming the immediate vicinity into a slip hazard reminiscent of a low-gravity hydraulics lab. We must calculate the precise angular velocity required to exploit centrifugal force for clean droplet separation, while avoiding the turbulent atomization that paints the mirror with a fine mist of stochastic regret. Consider a human hand approximated as a composite cylinder of radius r equal sign 0.045 meters, with the axis of rotation centered at the wrist joint. A thin, continuous film of distilled water adheres to the dorsal surface. The film has a uniform thickness h equal sign 1.2 times 10 circumflex minus 4 meters. The fluid properties are standard. Density ρ equal sign 998, text kg/m cubed, and surface tension sigma equal sign 0.072, text n/m. The local gravitational field is g equal sign 9.81, text m/s squared. Derive an expression for the critical angular velocity a omega_c at which the centrifugal body force overcomes the capillary retention force for a droplet of diameter equal to the capillary length. Subsequently, calculate the numerical value of omega_c in revolutions per minute rpm. As a follow-up constraint, calculate the maximum safe angular velocity omega_textmax before the radial acceleration surpasses the threshold, where a stray droplet achieves a ballistic trajectory exceeding a horizontal distance of x equal sign 0.35 meters, the average distance to the bathroom edge, given a release height of y_0 equal sign 0.80 meters. Assume the droplet detaches tangentially with zero vertical velocity component relative to the hand's center of rotation at the instant of separation, and air resistance is negligible. Determine the operational window for a tidy, ecologically sound hand-drying gesture. Report the final RPM window. The scenario begins with a thin film of water adhering to the surface of a hand following a routine wash. The hand is modeled as a cylindrical section with a radius of 4.5 centimeters. The water film possesses a uniform thickness of 120 micrometers. The ambient conditions are standard, with water density at 998 kilograms per cubic meter and surface tension at 0.072 newtons per meter. The initial inquiry seeks the precise angular velocity required to overcome the adhesive grip of surface tension. By equating the centrifugal body force acting upon a droplet of the capillary length to the retaining surface tension force, a simplification occurs. The mathematical derivation reveals that the critical angular velocity is simply the square root of the gravitational acceleration divided by the radial distance from the axis of rotation. Evaluating this expression yields a threshold of 14.76 radians per second, which converts to approximately 141 revolutions per minute. At this rotational speed, the forces acting on the water film transition from adhesion to expulsion. However, the analysis cannot conclude at the lower bound of detachment. A second constraint is imposed by the geometry of the surrounding environment. Should the rotational speed become too exuberant, the expelled droplets will achieve ballistic trajectories that clear the confines of the sink. The droplet is assumed to detach tangentially from the highest point of the circular path with an initial velocity vector parallel to the ground. The time required for the droplet to fall from a height of 80 centimeters to the floor is calculated to be approximately 0.404 seconds. Given a maximum acceptable horizontal displacement of 35 centimeters, the permissible horizontal launch velocity is limited to 0.867 meters per second. Dividing this linear speed by the radius of the hand yields a maximum angular velocity of 19.26 radians per second, or roughly 184 revolutions per minute. Therefore, the solution exists as a narrow, mathematically defined corridor. To execute a gesture that effectively sheds water without transgressing the boundaries of the ceramic basin, the wrist must accelerate to a rotational frequency between 141 and 184 cycles per minute. Outside this window, either the water stubbornly remains or the surrounding walls become an unintended canvas for fluid dynamics. The calculation provides a serene, empirical framework for a mundane yet universal human motion, ensuring both hygiene and the dry integrity of the surrounding floor space. Conclusion. The optimal operational window for a controlled, respectful, and floor-drying flick is between 141 revolutions per minute and 184 revolutions per minute. Below this, water clings via capillary adhesion. Above this, the bathroom transforms into a stochastic sprinkler system with a 0.35 meter danger radius. The solution provides a mathematical blueprint for a gesture that is both spiritually mindful and hydrodynamically precise. A content creator in a vast and sweltering desert, is attempting to solve a culinary physics problem that has foiled every other online personality they know. The objective is deceptively simple. Use a shiny metal sheet exactly 2 meters wide and 10 meters long to construct a solar parabolic trough. This trough must heat a narrow pipe filled with camel milk to precisely 70 degrees Celsius, starting from an ambient desert baseline of 45 degrees Celsius. If the milk gets any hotter, the proteins denature and the surface scalds, ruining the delicate texture required for the viral foam aesthetic the creator desperately seeks. The reflective sheet is formed into the shape of a parabola defined by the mathematical relationship, where the height y equals the square of the horizontal distance, x divided by 4 times the focal length f. The focal length is the distance from the very bottom of the curved mirror up to the central receiver pipe where the milk sits. This is a classic problem of non-imaging optics and solar concentration. The solar flux concentration ratio is defined as the true arc length of the curved mirror surface divided by the product of pi and the width of the receiver pipe. The receiver pipe is fixed at 4 centimeters in diameter to accommodate the standard flow rate of camel milk necessary for a continuous frothy pour. A series of previous experiments involving undercooked and tragically scalded milk have determined that the required concentration ratio to achieve that precise 25-degree Kelvin temperature jump is exactly 50. The question that determines whether the video ends in triumph or a molten dairy catastrophe is this: what exact focal length in meters must this parabolic trough possess to satisfy the 50-to-1 concentration requirement using the available 2-meter wide sheet? The mathematics behind this requires us to find the arc length of the parabola between the limits of -1 meter and +1 meter along the x-axis, since the total width is 2 meters. We set up the arc length integral s as 2 times the integral from 0 to 1 of the square root of 1 plus the square of the derivative of the parabolic function with respect to x. The derivative of y with respect to x is simply x divided by 2 times the focal length f. Substituting this into the integral transforms the equation into a standard hyperbolic form involving the natural logarithm. The resulting expression for the arc length s becomes the square root of the quantity 1 plus 1 divided by 4 times the focal length squared. To this, we add the product of 2 times the focal length and the natural logarithm of the sum of 1 divided by 2 times the focal length and the square root of 1 plus 1 divided by 4 times the focal length squared. We are given that the required concentration is 50 and the pipe diameter is 0.04 meters. Multiplying 50 by pi and then by 0.04 yields a required arc length s of exactly 6.28318 meters. Notice that this number is 2 times pi, a beautiful and entirely coincidental emergence of the circular constant within a parabolic geometry problem. However, this required arc length of 6.283 meters is significantly greater than the straight line width of the mirror, which is only 2.0 meters. This immediately tells the engineer that the mirror must be an extremely deep and sharply curved dish rather than a shallow, gentle trough. A shallow trough with a large focal length would have an arc length only slightly longer than its 2-meter width, perhaps 2.1 or 2.2 meters, which would result in a much lower concentration ratio and tepid, disappointing milk. To achieve an arc length of 6.283 meters, the focal length must be compressed dramatically, pulling the receiver pipe very close to the vertex of the parabola. We must solve the arc length equation for the variable f numerically, because the equation is transcendental and cannot be isolated algebraically. We test a value of 0.08 meters for the focal length. Calculating the first term under the square root gives a value of approximately 6.329. Calculating the logarithmic second term gives a value of roughly 0.405. Summing these two components yields an arc length of 6.734 meters. This is slightly too long, meaning our focal length is slightly too short, making the curve too steep and the concentration slightly higher, the target 50. We adjust the focal length upward to 0.09 meters and recalculate. The square root term now yields approximately 5.645 and the logarithmic term yields roughly 0.435. Summing these yields a total arc length of 6.080 meters. This result is slightly too short, meaning the curve is not quite deep enough and the concentration would fall just below the required 50. The true answer lies almost exactly halfway between these two tested values. Interpolating between the results for 0.08 meters and 0.09 meters brings us to a focal length of 0.083 meters. That is 8.3 centimeters. When the parabolic trough is bent to a focal length of exactly 8.3 centimeters, the distance from the vertex of the shiny metal to the center of the milk-filled receiver pipe is less than the length of a typical human thumb. The 2-meter wide sheet of reflective material curves upward, sharply cradling the pipe in